So let's do another example dealing with a removable discontinuity, but this one's going to be a little bit more complex. So in this case, f of x is this piecewise function here, and we have to show that this function is not differentiable at this x value of 2. So if I graph this function now, remember the function in the first example was just x squared minus 4 over x minus 2, and f of 2 was not defined. Well, in this case, f of 2, because it's a piecewise function, is defined because we're saying at an x value of 2, the y value is going to be 5. And so now there's going to be more work because we can work with that limit a little bit more. So first I'm going to graph this. Now remember, this x squared minus 4 over x minus 2, this simplified to a line that was x plus 2, and then at an x value of 2 there was a hole. So if you think about it, we can rewrite this piecewise function as just x plus 2 when x is not equal to 2, and then 5 when x is equal to 2. Because that hole is happening at an x value of 2. But for all of the other x values, so if we redraw that line again, so there's a hole there at this x value of 2. Notice for all of the x values other than 2, it's just this line, x plus 2. Right? And so we don't really have to write this whole function here for x values not equal to 2. We could just write x plus 2 when x is not equal to 2. So both of these would mean the same thing. And then notice that at an x value of 2 now, there's a y value of 5. So remember, this hole here was at a y value of 4 that we mentioned in the previous example. This hole happens at a coordinate 2 and 4. And now at an x value of 2 for this piecewise function, there's a y value of 5 up here. So this coordinate is 2 and 5. So that's the graph of this piecewise function here. And we now have to show that this function here is not differentiable at an x value of 2. And remember, to show something or to show a function is not differentiable at a certain a value, we got to show that that definition of the derivative, this limit here, f of a plus h minus f of a all over h, does not exist. So if we plug in, notice the a value is 2 that we're working with, so we'll have 2 plus h minus f of 2 all over h. So notice in the example before, this f of 2 was not defined. And so we didn't have to go further with this limit, but now f of 2 is defined. Notice it has a y value of 5. And so there's going to be more work with this limit. It's what I was referring to before. So we'll have the limit as h approaches 0 of f of 2 plus h. Now notice that h can be approaching 0 from the negative and the positive side. And no matter which side it's approaching, notice that you're going to have 2 plus a very small number. And remember, what the piecewise function simplified to was it was x plus 2 when x is not equal to 2, and it was 5 when x is equal to 2. So notice that this part here is always going to be an x value other than 2, because it's as h is approaching 0, so there's going to be a really, really small value for h here. So it's going to be 2 plus a very small value, or if we're approaching h from the negative side, it's going to be 2 minus a very small value. So this here, this 2 plus h, we have to plug it into this function, because it's going to be an x value that's not equal to 2. It's going to be very close to 2, but it's not going to equal 2. So we've got to plug it into that function right there. So it would be 2 plus h plus 2. That's what f of 2 plus h is, if we plug in 2 plus h for that x value. Minus f of 2 now is defined. It's 5. So this is going to be a 5, and then this is going to be all over h. And so now what we're going to get is the limit as h approaches 0. Notice that we'll have, this would simplify to h plus 4 minus 5. So this would simplify to h minus 1 all over h, like that. And so now, this limit here, limit as h approaches 0 of h minus 1 over h, what we can do is we can graph this function. Going back to advanced functions, this is just a linear over a linear function. It's a rational function. But if you didn't want to graph it, what you can do is we can approach h from, so let's actually write it. We could approach this h value 0 from the negative side. And we can approach this h value of 0 from the positive side. Because notice we can't plug in 0 for h because it's going to make that denominator equal to 0. So we got to approach that h value 0 from the negative side and the positive side. And if you didn't want to graph this function here, you can just make a table. So if we're approaching an h value 0 from the negative side, we can use like negative 0.1 and then negative 0.001, negative 0.0001. We could just get closer and closer to this h value 0 from the negative side. Then we can make a table for this. We can approach that h value 0 from the positive side. So 0.1, 0.01, 0.001. Right? And we can just plug in these values for this function and see what's going to be happening with those y values. Notice these are going to be infinite limits here. And what you're going to get, so I'm actually going to graph this function here. So h minus 1 over h, there's going to be a vertical asymptote at 0. There's going to be a horizontal asymptote at the ratio of the leading coefficients. I'm going back to advanced functions now, the rational functions chapter. It's going to be a ratio of the leading coefficients, 1 over 1, which would be here. So this is going to be at a y value of 1. And then notice that, so there's going to be a vertical asymptote, a horizontal asymptote. Notice there's going to be an x or an h-intercept of 1. That's going to make the numerator equal to 0, which is going to make the whole function, or the y value, equal to 0, right there. And so the way this is going to look is like that. Again, you don't have to necessarily know how to graph this. You can make the tables like I mentioned before. But if you look at the graph here, notice that as we approach 0 from the negative side, notice that the y values are approaching positive infinity. And then as we approach 0 from the positive side, the y values are going towards negative infinity. So those are the values you should get in those respective tables as well. But graphically, this function looks like that. Okay, so now what does this mean? So notice that as we approach this value of 0 from the negative side, it's going towards positive infinity. As we approach it from the positive side, it's going towards negative infinity. It's approaching different values, which means that this limit does not exist, right? It's undefined. And so because this limit here is undefined or does not exist, we just proved that this function is not differentiable at that x value of 2. Notice this is another case of a removable or point discontinuity. So we can tell that it's not going to be differentiable just because it's discontinuous, I mean. But to show the work, we got to do this. And notice there's more work than that first example because we made the function, which was a piecewise function, defined at that x value of 2. Versus before, it was undefined, so we didn't have to go all the way like this. Now, I want to spend the rest of the video talking about the intuition of why we got this positive and negative infinity as it relates to the graph. So we already show that it's not differentiable algebraically, but I want to spend a little time in getting you to understand why this is positive infinity, why this is negative infinity. It's going to be a bit of a complex explanation, but I'm going to do my best. So remember, if we go back to the fundamentals of the difference quotient, what is the difference quotient? Notice that it's the slope of a line between 2 points where one of the points is f of 2, so it's this 2 and 5 in this case. And then the other point is a point that's really, really, really close to it. And the reason why we're getting the slope of a line with 2 points that are really close is that it's going to give us an approximation of what's the slope of the tangent going to be at this 2 and 5. Notice this point is by itself, so it's hard to tell what the slope of the tangent is going to be. And so going to here, notice if we're approaching this h value 0, if we approach it from the negative side, so like negative 0.1 or negative 0.001, etc., we're just getting closer and closer to 0 from the negative side. Notice that h value is going to be negative. It's going to be a very small negative number. And so going back to here, what we're going to be doing is this point is 2 and 5. This point here is going to be 2 minus a very, very small number. 2 minus a very, very small number. And notice that for this function here, any x values other than 2 are going to fall on this line. Right? It's only at that x value of 2 that we have this y value of 5, but any other x value, even if it's really close to 2, it's going to be on this line. And so if we're approaching h value 0 from the negative side, again, this is going to be 2 minus a very small number. So notice that we're going to have points here that we're approaching this x value of 2, but from the negative side. And so notice that if we draw a slope of a line, we'll have that. And as we get closer, we'll have that. As we get closer, we'll end up having that. So notice that slope, it's a positive slope. And then as we're approaching this x value 2, as that h is getting smaller and smaller, we're getting more and more positive, right? So it's a positive line initially, and then it's just becoming more and more positive. It's becoming more and more steep until it's approaching that vertical line, right? And so that's why, because it's positive and it's getting more and more steep, that's why this limit here is going towards positive infinity as h approaches 0 from the negative side. Because if h is negative, then that point close to this one is going to be on this side over here. So we're getting closer and closer, and that slope is always going to be positive. It's going to get more and more steep, so it's going towards positive infinity. Versus the other way, as we approach 0, as we approach an h value 0 from the positive side, notice that with the difference quotient, we're going to have this point 2 and 5 again, but we're going to be finding the slope of a line with an x value that's 2 plus a positive value, a very, very small positive value. And so we're going to be finding the slope between this point and a point to the right of 2. So what's going to be happening is we're going to have a slope here, but we're going to start that as that h value goes towards 0 from the positive side, it's going to start going closer and closer to that x value of 2, but from the positive side now. So notice that in this case, that slope is always going to be negative. It's going to start getting more and more steep towards the negative side, but nevertheless, it's always going to be negative. So it's going to start at a certain negative value, then it's going to become a larger negative value, larger negative value, larger negative value. It's going to approach that vertical line, and that's why here this limit is approaching negative infinity. So that's where we're getting these values from. So just wanted to explain graphically what is going on. Remember your fundamentals for a difference quotient. All we're doing is we're finding the slope of a line between 2 points, between the point that we're looking at and other points that are very, very close to it, right? So just wanted to explain how we got that, how it makes sense graphically. It's not as important, but just to increase your understanding. Hopefully that explanation wasn't too bad. But the most important thing is that we showed that this limit here does not exist. So we showed that this function is not differentiable at that x value of 2.